SwayamPrabha. Digital India. Educated India.
Hello all. In this video we'll be discussing about the classical laminate theory. In previous video we showed that for a laminate we do the bonding to improve the bending stiffness, but for us to analyze to see once applied a load how the laminate deforms, or once we know the deformation of a laminate how do we find the loads applied on it, we need a theory. So we also identified that we need a theory where we can apply the deformation compatibility, the stress strain relation, and the equilibrium simultaneously. We said that classical laminate theory is one of such theories where we can apply these three simultaneously. So let's start looking at the details. So in this theory, what we are essentially doing is we, instead of working with a 3D elastic problem, meaning the stresses and strains as we know are three-dimensional in a laminate. So instead of dealing with a three-dimensional elastic problem which is much more difficult to solve, we make some simplified assumptions which transform this 3D elasticity problem to a 2D mechanics of materials problem. So in this video we will be going through what are these assumptions we make and how we can simplify these analysis. So there are other names for this classical laminate theory called the classical thin lamination theory or the classical laminated plate theory. But in this course we'll be going with the classical laminate theory which is widely known. So the way we will approach this theory is we'll go it in three different steps. First we'll be starting by recapping what we already know about the stress strain relations in a lamina. So when we discussed about micromechanics of lamina, we already discussed what is the relation between the stress and strain. So that's what we'll recap, and after that we will look at the stress and strain variation through laminate thickness. So we'll make some assumptions in the laminate, and using those assumptions we'll show how the stress or the strain varies with the thickness of the laminate. And lastly, look at what is the relation between the forces and moments to the strains and curvatures in the laminate. So let's start with the first step where we review what is the stress strain relation for the kth layer in a laminate. So we are looking at the orthotropic materials. We said these reinforced composites can be considered as orthotropic materials because the properties are different in different directions. And we have simplified in plane stress, meaning that there are only three non-zero stress components. For this, we have shown what is the relation between the stress and strain using this stiffness matrix. This is the reduced stiffness matrix. But mind you, these are written in the principal material coordinates. What is principal material coordinates? Meaning that the stresses and strains we are looking along the fibers and perpendicular to the fibers. So these directions of along the fibers and perpendicular to the fibers, we call them as principal material directions. And if we have chosen this coordinate system for our stresses and strains, then we end up with this stress strain relation for the in the principal material coordinates. But we see that more often it is not the case, meaning that there is an orientation angle theta. Once we have this orientation angle theta, how do we define the stresses and strains along these new directions? For that, we have used transformation matrices and showed the stresses in the body coordinates. Body coordinates written in terms of x and y, uh, in contrast to the 1 and 2, which are the material coordinates. So here we have written in terms of this transformed stiffness matrix. Okay. So these are the stress strain relations either we are looking in the principal coordinates or the body coordinates. So essentially, if we are focusing on the kth layer, which means one of the layers in a laminate, then for that layer, we are saying that we are looking at the kth layer in a multi-layered laminate. Then if you are looking at the kth layer, the stresses are related to the strains using the transformed stiffness matrix, which we represent using Q bar. So let's keep this in mind because we will use these concepts a few slides later, where we'll invoke these to come up with the stress strain relations in laminate. Now let's start by looking at what are the assumptions we make in the classical laminate theory. Most of these assumptions are for the deformation of how a laminate deforms. So the first one is about, we are assuming a perfectly bonded lamina, meaning when there is a bond between two layers, we say that this bond is perfect. If there is any imperfections, what it means is while bending there can be slip happening between these layers. So for now we are saying that there is no slip and there is a perfect bond. In addition to that, we also make one more assumption saying that these bonds are infinitesimally thin. What does that mean? Let's say we are looking at two layers which are joined by bonding at the interface. So if you zoom in at that place, actually there is a small thickness because we are applying a glue where the properties are different. But for now what we are saying is this thickness is negligible or infinitesimally small. So the reason why we have this infinitesimally thin and non-shear deformable assumption is to ensure that when we look at displacements happening at the interface, we need to ensure that the displacement just below the interface and above the interface are continuous. How do we ensure this continuity? By assuming that this thickness is very thin. What happens if the thickness is large? If the thickness is large, then since there is a gap, now you can have shear stress, which means shear deformable at the interface, or maybe they are separated. So which means going from one layer to the other layer, we could see either discontinuity or these shear deformations happen, which is not permissible once we assume that they are thin. But more importantly, there is another assumption where we focus on the normal to the mid surface. So let me show you this with an example. So let's look at this book and focus on this area. Okay. In this area, where is the mid surface? Mid surface is a line at the center, like half thickness, right? Now, where is the normal to this mid surface? So let's focus on two normals. Normal is the line perpendicular to the mid surface. So since we said the half thickness is the mid surface here, the perpendicular to that at this point, for example, this edge is one of the line perpendicular to the, this is the normal which is perpendicular to the mid surface, and this is another normal which is again perpendicular to the mid surface. Now let's see what happens to these two normals when I deform or bend this book. When I bend this book, there is a stark difference between how this edge deformed versus the other edge deformed. Can you notice and see what is the difference? Are these both straight lines after deformation? More or less, the answer is true. So this is straight after deformation, and even this is more or less straight after deformation. But the question is, are they still perpendicular to the mid surface or not? So if you focus on this edge, you will notice that this is more or less perpendicular to the mid surface even after deformation. But can we say the same to this edge? The answer is no, because you will notice that this edge is no more perpendicular to the mid surface, meaning at this edge you see some shear deformations happening, while at this edge you don't see any shear deformations happening. These are the kind of assumptions we'll be discussing. Let me show it. So the first assumption is, we said these normal will remain straight and perpendicular to the mid surface, both before and after deformation. Meaning, let's say this is the deformed shape, and now we are drawing these normals. Let's say this is the mid surface. What we are saying is, even after deformation, this mid surface or the and this edge is the, let's say, the normal, they are perpendicular even after deformation is what the assumptions we are making. They remain straight as well as they remain perpendicular to the mid surface after deformation. There is another assumption we make, saying that this normal is constant length, meaning the thickness of this or the length of this normal won't change before and after deformation. In both conditions, it will have the same length. These assumptions are effectively the Kirchhoff hypothesis. So they call it as the Kirchhoff hypothesis for plates or the Kirchhoff law hypothesis for shells. But these are all done it in two dimensional. If you take it down into one dimensional, this is the simple beam theory we discussed, where again we have the similar kind of assumptions saying that the normal remains straight before and after bending, and the normal is perpendicular to the mid surface or the midline before and after bending. And it also says the length of the normal is remaining constant before and after bending. But now let's look at how these assumptions will affect our strains. So starting with these first assumptions about the normal, here we said that these remain perpendicular to the mid surface. And with the book I showed you, because of this assumption, we assume that there is no shear happening. So again, if I have to repeat it, we said that this is the assumptions we are taking in the hypothesis we have here, where there is no shear deformation on this edge, but whereas on the other edge is what we have a shear deformation, and this is not a part of the classical laminate theory. Actually, there is an advanced theory next to the classical laminate theory, that's where we assume this shear deformation. But for now, we are focusing on this edge where there is no shear deformation. Okay, what does that help us? It says that the shear strains are 0. So we are talking about x and y is the plane we are looking at, but out of planes are gamma xz and gamma yz. We said both of these strains, the shear strains or the out of plane shear strains, are 0. And from the second assumption where we said we have constant length, what it essentially means is the strain in the z direction or the out of plane direction is 0. So with these three assumptions, we can say we are in a plane strain situation where the out of plane strains are 0. So we can only focus on the three components of strain, which are gamma epsilon x, epsilon y, and gamma xy. But now let's see with these assumptions how we can talk about the deformation or write some expressions for the deformation. Let's assume a plate with a small thickness. And now let's define the coordinates. This is x, y, and z direction will be downwards. So this is the notation we will be following throughout this classical laminate theory. So pay attention that the z is going downwards. And corresponding to these three directions, we will also define displacements. Along the x direction we have displacements u, along y is v, and along z is w. So u, v, w are the displacements at each point along this coordinate axis x, y, and z. Now let's focus our attention on one of the edge. Let's say this is the edge AD. So let's focus on this edge AD and see what are the deformations on that line AD. So here I am showing you again the same, the line A and D, but in this line we have point B which falls on the mid surface, and C is some arbitrary point at a distance of ZC from the mid surface. Okay, and here as you can see Z, again the Z is going downwards, but it is 0 at the mid surface. Okay. So with these, we have shown both the undeformed cross section as well as the deformed cross section. Meaning, like, let's say if you are focusing on this point B, which is at the mid surface, we said this point B after deformation moved to a new point here. And what is the displacement along the x direction? That is given by u naught. So you notice that there is a subscript of naught. This subscript is used to denote that we are discussing about mid surface. So the 0 here means mid surface. Okay. So u is the displacement of this point B along the x direction. Now let's focus on this point C in the deformed configuration. How can I know what is the deformation of this point C along the x-axis? That can be written as, in terms of the mid surface deformation u naught minus zc times beta. What is zc? That is the distance between B and C. So here we have shown it, and here too again I can repeat. So this is this distance, and then what is beta? Beta is the angle of rotation. So zc times beta will give you this length, and since it is going backwards, we have this negative sign. So u naught minus zc times this angle beta. But now the question is, what is this angle beta? We notice this, the angle, the same angle beta is also making here. So this itself, this also is angle beta. But what is this angle? This is the angle the mid surface is making with the x-axis. So how can we relate that? We can write this as dou w naught by x. What is w naught? W naught is the deformation in the z direction. So this is the first differential of this deformation w with respect to x will give you beta. So I hope everyone is getting it. So we got this expression from looking at this geometry here, saying that there is a displacement u naught at the mid surface, and because of this rotation we have this product zc times beta. But beta we noticed is the slope of the mid surface. So at point D the z value is t by 2, the half thickness, and at A what is the value of z? It is minus t by 2. The reason being, now we have defined z axis going downwards and it is starting at the mid surface. So the value of z is minus t by 2. Okay. So this should give us the displacement of any point across the thickness. So there is one important point we need to emphasize, saying that this edge AD, which was straight initially, after deformation it was straight, because it is again part of these classical laminate theory assumptions which we just discussed in the previous slide. We said it will be straight before and after, so this line AD is straight even after deformation. And we also mentioned that this deformed line AD will be perpendicular to the mid surface both before and after, and that's how we came up with this beta relating with the deformation W. Okay. So in this, let's say if instead of looking at this edge AD, we look at another edge on this edge, then we should be able to write in terms of the y-axis deformation, which is V. So meaning now similar to U, I can now write for V. So V again I can write in terms of displacement in the mid surface times z times the first derivative with respect to the displacement along z. And mind you, here again we are writing this with respect to naught. The subscript naught represents the deformations at the mid surface. So in summary, what we are trying to see is, once we know the deformations at the mid surface, which are u naught, v naught and w naught, we should be able to write what are the deformations at any other thicknesses, which means we know u and v at all other points across the thickness. Now that we have seen expressions for the deformations, now let's move into the strains and see how we can write those strains in terms of these deformations. Okay. Here we invoke one more assumption in the classical laminate theory, saying that we are looking at small strains. When we look at small strains, we know what are the strain displacement relations, which are given in terms of first deformations u and v. So we are able to write this strain vector epsilon x, epsilon y, gamma x, y in terms of these deformations u and v, the differentiation of those deformations. So these are the deformations we just showed in the previous slide. So once I plug in these in the strain deformation expressions, I can write them as epsilon x is written as dou u naught by dou x minus z times the second derivative of the deformation w. These three expressions we will write it in the matrix form now, starting with these expressions, the first terms, the dou u naught by dou x, dou v naught by dou y, and dou u naught by dou y plus dou v naught by dou x. So essentially we are looking at the terms where there is no dependence on z. So because the second terms all depend on z, that we have left it. So what do these give? These are the strains occurring on the mid surface. Okay. Now looking at the remaining terms, we can all capture them, and now notice that these are, since we are looking at the second derivative, these are the curvatures. So we have curvature kx, ky and kxy. Actually this kxy is also called as twist curvature. Okay. As you can see, these all are written in the second derivatives of the deformation in the z direction. And finally, once we combine this, add these two vectors, this should give the strains. So here we get the strains as sum of strains of mid surface plus z times the curvatures. Okay. So with this we are able to write the strains at any point on this laminate, because we just need to know what are the strains in the mid plane. Once we know that, we can use the curvatures to get to the strains at through thickness any point. Now that we are able to show you how we can write the strains, the last bit of the information is to bring in the stresses. How do we bring in the stresses? There we invoke the stress strain relation. So here is the strain relations which we derived just in the previous slide. And now if I bring in the stress strain relations, where you recall stress in the kth layer, we wrote it in the stiffness matrix, the transform stiffness matrix times the strain. So this is the transformed stiffness matrix. And these are the stresses in the kth layer, and the strains in the kth layer we wrote it in terms of the mid-plane strains plus k times the curvatures of the mid-plane. So there is a small difference between the way we look at the strain relations versus the stress strain relations, because what we see for these strain relations, these are applicable for the whole laminate, so across the complete thickness of the laminate. But the second expression is only applicable within each lamina. The reason is because this stiffness matrix what we are writing here is only for a kth layer. But if you go for the K plus 1th layer, then you will come up with a new stiffness matrix because it might have different material properties, different orientations. So the stiffness matrix will change. So this is a very crucial point one has to remember when we write these strain relations versus the stress strain relations. And this difference will also explain what is the variation of the strain across the thickness and the variation of stress across the thickness. Let's see how we can explain them. So let's consider this laminate. Here we are showing you a 4-layered laminate made from 4 lamina. Now let's see what will be the variation of the strain. So previously we have showed you that the deformation is straight line. So the vertical line or this normal AB, before and after deformation it is straight line, and after deformation we said it is perpendicular to the mid surface. But when we wrote these strain relations we got linear relations, meaning the strain varies linearly from top to the bottom of the laminate, which is shown here. So the strain distribution is linear. Okay, but can we say the same about the stress or not? The answer is no, because each layer can have a different Q matrix, meaning let's think of it like each layer is made up of one characteristic modulus. So the modulus can vary because let's say for material 1 this value is 1, for the material 2 it is slightly more, and for material 3 this is slightly less, and for material 4 maybe it is much more stiffer. Meaning at each layer we are saying the stiffness properties are different. But how did we get stress? We got stress by multiplying the stiffness matrix times the strain, meaning in each layer it will still remain linear. So this is the stress distribution in layer 1. So in the layer 1 we still have a linear relation because all these relations we have written are linear. But the point is this relation is only applicable for layer 1. You cannot apply it for layer 2 because here we are writing it in terms of, let's say, Q for 1. But here Q2 times strain. So the strains might be linear, but since we are going from Q1 to Q2 which are very different, there is a discontinuity at the stress at the interface. But previously, is there any discontinuity? No. So at the interface between two layers, the displacement is continuous, strain is continuous, but for the stress there is a discontinuity. That's point 1. What else can we say? We can now say that uh, it is linear, stress varies linear. Within each layer. But there is a, so we need to underline that within each layer, because that doesn't mean that stress is varying across the layers, because once we move from layer 1 to the adjacent layer there is a jump in the stress which needs to be accounted. So this is how the stress variation and the strain variations are very different in a laminate. And now let's summarize what we have discussed. We started by looking at what is the relation between the stress and strain. We said this is related with the transformed stiffness matrix for the kth layer. But later we made a series of assumptions for the deformation, mostly for the normal to the mid surface. We said it remains straight before and after deformation, it remains perpendicular to the mid surface before and after deformation, and it remains the same length both before and after deformation. Because of all these assumptions, now we are able to simplify the stresses and strains only to three components. And then we are also able to write these deformation expressions in terms of the mid-surface values. And later we also showed you the strain displacement relations which came to be linear. Using those, we also showed you the stress strain relations which are again linear. But most importantly, we said the variation in the strains and stresses are slightly different. Strains are continuous or they're varying linearly across the laminate, the complete thickness of the laminate. But whereas for stresses, within each layer of the lamina, they are straight line or varying linearly. But once you move from one layer to the other layer, there is a discontinuity in the stress. That needs to be taken into account, and that is one of the reasons why there are failures occurring at the interface. So with this we'll conclude. Mind you, we haven't completed the classical laminate theory. In the next video, we will use these stress strain relations to bring in how it relates with the applied loads and the moments, which is pending and which we'll show you in the next video.